Hello, and welcome to another class of data science. Today we'll be looking at the iris dataset, and the objective of the class will be to first introduce you to the dataset, to set up the problem statement and the objectives that we're trying to achieve with this dataset. I'll then provide you with some key insights as to how you would train your model, and finally, I'll come up with an example of the model you could use to train for this dataset. So what is iris dataset? Iris dataset is a dataset of 3 different species of irises: Setosa, versicolor, and virginica. And what you're trying to do is using the characteristics of these flowers to classify which flower it is without actually seeing the flower. And those characteristics are here. So this is how the dataset looks like. You have the sepal length right here. You have the sepal width, you have the petal length, and the petal width, and then you have the 3 species that we've mentioned here. So as a good data scientist, you should first understand what does sepal length, sepal width, petal length, and petal width mean. And here's a pictorial depiction of what it means. So what we have here is the sepal right here. So we'll be looking at the length of the sepal as one of the variables we'll use to predict the species. We'll also look at the width right here. We also have the petal, and again we have the length of the petal, and we have the width of the petal. So in total we have 4 variables that we'll use to predict whether a species is Setosa, virginica, or the third type. Now, before we start, what you should try to do is first try to plot the different characteristics that we have. So right here, we're showing a 2D plot where on the left-hand side, we see the petal width, petal length, sepal width, and the sepal length plotted against the same characteristics at the bottom. And right away, we notice something interesting with this data set. And by the way, this part of what we're doing here is what we would call data exploration. Data exploration is very important in every data science project. You should always do it before you start doing any modeling, because it gives you insights and into the data, and perhaps you will start understanding what to look for. So in our case, what we notice is that we have these very defined chunks of characteristics, and the red represents Setosa, blue represents the versicolor, and the purple represents the virginica species of the irises. And so what we see is that in all of these plots, or in many of them, the Setosa species is very well defined and can be easily isolated from the other 2 species. And what we call it linearly separable. So what that means, we can draw a line between the Setosa iris and the other 2 species of irises. So in our case, it makes it very easy to use any linear type of model if you just wanted to understand whether or predict whether the type of flower is Setosa versus the other 2. But in our case, because we want to predict all 3 different types of flowers, we won't be able to use any linear type of model. In our case, the linear types of models includes linear regression, logistic regression, and so we'll have to use something more interesting or nonlinear. And so what types of nonlinear models exist there? Non-linear. So one is decision trees. Another one is neural networks. And there are many more. But we'll focus on the first two, decision trees and neural networks. For the purpose of this lesson, I won't be drawing out the decision trees. Instead, I'll just focus on the neural networks and how we could apply them to this data set. So the neural network, just to give you a review, it takes in an input of features, and in this case, the features would be the petal length, the petal width, the sepal length, and the sepal width. Those features go through a model, which we call the neural network. And on the other side, we get a prediction. And usually the prediction is an output that gives you the score of probabilities. So in our case, we have three different types of species, and so it would say, for example, given those features, hypothetically 1.5, 0.1, and 3. On the other side of the neural network, what we should get is the probability. So what is the probability of it being the setosa iris, versicolor iris, or the virginica type of iris? And sorry for those technical difficulties here. And the probabilities would all have to add up to 100%. So in this case, this could be, I don't know, let's say this is 57% that this is a setosa flower, 3% that it's versicolor, and 40% it's a virginica iris. So then in our program, we'll say that we'll choose the highest probability, and in this case, we know that the flower that corresponds to these features over here is most likely a setosa. So the immediate question is, how should this part look, right? Because we already have our inputs and they are in the number format. And let's go back to the top. So the inputs are already in the number format. So we don't have to worry about them too much, although there's one thing we must do before we start training. The problem we have is that our output is actually written as words. So we'll have to convert the words into numbers so the machine, or in our case the neural network, can train. So we go back to our model, and so let's start drawing out the details of the model. A neural network, as you've learned in class, looks very similar to linear regression. Indeed, it's actually several different regressions stacked on top of each other. And here's what we'll have. Let's say this is the input, and we have 4 different features in our input. We'll construct the following hypothetical neural network. Well, in the first layer, we'll have 4 neurons. In the next layer, we'll have 3 neurons. And then there will be a layer which we call softmax. And softmax, what softmax does, it brings a continuous value of continuous values into the probability domain, so that what we get is we get those probabilities here, so they all add up to 100%. And all of these neurons are going to be connected to all of the input features. And same for this neuron and this neuron, and then it becomes messy very quickly. But you get the point. So now we have a hypothetical architecture of a neural network. Once again, this is called the input layer. This is called the first layer, and we refer to them as hidden layers. So first hidden layer, second hidden layer. We don't. Some people refer to softmax as being a layer. Some people don't. I usually refer to hidden layers as those with weights. So these connections here actually have weights. So those are the things that are trainable. So after the softmax, we have the output, which is going to be the 3 different species. Now, as we see, our output is a 3-dimensional output, right? But in our data set, we have the species represented as words. So what we'll have to do is convert them into what we call one-hot encoding. So we have 3 different categories: setosa, versicolor, and virginica. And what we do is we assign for each one and one-hot encoding. So all the flowers that are setosas are going to have an output that we try to match as such. And then, so to be more illustrative, if you go back to our data set, we'll try to replace this with the following: 1, 0, 0, 1, 0, 0, and so on and so on. And then let's say for a different type of species, the hot encoding is going to be 0, 1, 0, and it'll be different for the third type of species. And why? What does 1, 0, 0 represent? We can think of them as probabilities. So right here, we were outputting a probability, right? Which is equivalent to 0.57, 0.03, and 0.4. This is what the model would predict. What we try to do, and what we call is trying to hit the target. In our case, if this flower is indeed the setosa, so the S, then our target, or what our model should ideally predict, is 1, 0, 0. So this should be increased to 1, this should be decreased to 0, and this should be decreased to 0. And so that's why we have to convert all the species names into one-hot encoding. And at this point, you're ready to start training.